Okay, so we'll do this talk. I will do this talk together with my business partner Gaute Lambertsen, who's in front here. My name is Christian Moen. I worked with a commercial search engine company called Fast for 10 years. That company was acquired by Microsoft. So at that time, I left Microsoft and started a company called Atilika in Japan in 2009. I'm also a newbie Lucene and Solr committer, so I've mostly been working on Japanese language support. My business partner Gaute, he is also Norwegian, so we're two Norwegians in Tokyo. His background is he's been doing research work at Nokia and also at the Sony Group company, and he joined last year. So about our company, we're a small company based in Tokyo. So even though we are small, our customers are typically very, very big companies. And some of them are in Japan, but we also have customers in Europe and the United States. So we focus on innovation and we help companies innovate using new technologies and offer new ideas. So we're software engineers, but we also like the business side of things. And our core competency is search, NLP, and big data. And we all are big supporters of open source software. And we have been working on, we donated Japanese language support to the Lucene and Solr projects last year. Okay. So about this talk. The topic of this talk is very, very big, natural language processing in Lucene and Solr. We have selected a few topics that we think are important in this context, but we're not going to cover everything. It's just too wide and too big. So we're going to start out by reviewing at the very high level what the search engine does, and then we're going to introduce you to some languages, some you may know, some you may not know, and also illustrate some of the complexities with natural language that we need to deal with in search. We're also going to introduce just very briefly some measurements for search quality. And then we're going to go into the linguistics functionality in Lucene and Solr and how these things work and frameworks and so on. And then we're going to talk about a bit about the NLP ecosystem that surrounds Lucene and Solr. And we're going to talk about some closing thoughts about the bigger picture of natural language processing and search. Along the way, we also want to be hands-on and show you some examples of how things actually work with code. So we would like to do these for hands-on. So the code for all these things are available on GitHub, and we will get back to that later on in the presentation. So I will now let my business partner Gaute do this next section of our talk.
Good morning, everyone. I'm Gaute. I'm working together with Christian in Tokyo, and I will be assisting him at some couple of sections in this talk. So we are going to talk about natural language processing, but we are doing it in the context of the search engine. So we thought maybe it would be natural to first take one step back and just look a little bit at what happens with the search engine. So we go straight to a very simple example, but let's say we have two documents, very simple setup for this example, but we have two documents and we would like to index them in our search engine. So we have a document first, which we just, the first one, number 1, sushi is very tasty in Japan. And we have another one, visiting the Tsukiji fish market is very fun. So these are with English text. And before we can put them in the index, we would first start to split them up into manageable pieces. So we start with doing tokenization on all the words in the documents, one at a time. So for the first one, we see we have sushi is very tasty in Japan, and so on for the other documents in that we're going to put into the index. Next, we do some basic processing on this, so that so typically we will we will normalize some of the terms. So here we're taking away the uppercase words, putting everything into lowercase. And then we are left with these tokenized documents with normalized tokens. So next step, we put it into an index. And we can see here that this index, we map all the words that we have in the documents that we're indexing to point to the documents where they appear. So sushi is in document number 1, is in document number 1 and 2, Japan in document 1, and Skiji in document 2, and so on. So next, we now have an index with some documents, and we would like to see if we can find some information and get it back to the user. So, for example, we have a query, very tasty sushi. Any documents that makes a hit on that? So for this example, we are doing and we are taking the and between all the terms in the query, and so it means that we need an exact hit to find. We need all the terms to hit in a document for this example. So here we have sushi, very tasty, all appear in document number 1, and we see that varies also shows document 2. Adding them all together, we find that document 1 is the answer to the query. Now we have another one, visit fun market. So we do the same thing again. We split up all the words in the query into tokens. We add them together, and we start looking in our index. So first we have fun and we have market. We seem to be doing okay. And then, so visit here, we see that we don't have that in the index. So we see that it doesn't match with the visiting, and so we get no hits. Because as in this example, we need to match all the terms. So what's the problem with this picture? So the problem, what we've been thinking here is that the search engines, they are not just magical machines that you can just put something in and then you get something out, and we have to think a little bit about what we put in and how to get it back. So what we do is they match terms in queries. So they have to be matched against the documents, and then for a bigger example, we will order the matches by rank and find the best documents. So the key takeaways from this part of the talk is that the text processing itself might affect the search quality in a big way. The reason for this is that it affects the matching, and so it means that if we put in garbage into the system, and the only thing we're going to get out is probably garbage, and it's going to be difficult to find the documents that we would like to find. So in order to achieve the magic of the search engine experience, we would need to do something with the text here to get better quality. Okay, so that's a little bit of background on the search engine and some of the problems from a very high level. So next we will talk a little bit about natural languages and search, and what we can do to make the quality in our searching experience better. So to do it, we will present some we have just selected a few languages that have some differences, and we will just have a few examples and look at what happens, what we can do, what we need to think about for these languages. So I'll start off with English. So we have an example sentence here. So, pale ale is a beer made through warm fermentation using pale malt and is one of the world's major beer styles. So that That should be okay. Simple enough. But what do we do with words like the world, for example? So how should we, do we want to have a hit on world, or what do we do with it? We have other things. What about style? Should we get a hit on styles? Or what about ferment? Should it match fermentation, and so on? So we have to think a little bit about how to process this to get good results back. Okay, but still seems to be manageable. Go to the next one. So, okay, German. This is, looks a little bit more complex. See, I see if I can try to read it out. Das Oktoberfest ist das größte Volksfest der Welt und es findet in der bayerischen Landeshauptstadt München. So I'm not, yeah, it sounded German to me, but I'm not completely sure. Anyway, it means something like the Oktoberfest is the world's largest festival and it takes place in the Bavarian capital Munich. So, what about this? There are some things here we didn't see in the English example, so what do we do with these kind of letters that are typical for German? I think it's I, Ö, and yeah, I'm not sure the double S here. And what about this? We have combined words like Hauptstadt. It means capital, and then you have from a regional capital, which in Germany they put the words together, so you have a Landeshauptstadt. Do you want to have them to match each other, or not? We even look at other words here. There are in German typically many words are combined together, so you have compound nouns. For example, Oktoberfest is a big festival. It's in October, so wouldn't it be natural to get a hit on October and festival, for example? This will be difficult with this kind of situation. Okay, so let's go and look at another language, see if we have something else. So French, and it's getting getting a little bit more difficult. Le champagne is, I think, actually, Christian, can you help me out here? I think I think you have to take care of the French one. Yeah, I think so. Please, there you are.
Le champagne est un vin pétillant français protégé par une appellation d'origine contrôlée. Does that sounded French to you guys? Then I'm happy. So it basically means that champagne is a French sparkling wine with a protected designation of origin. So with this French example, we have similar troubles. Like, how do we deal with these sort of characters? Do you want this pétillant? Do we want pétillant without this accent aigu, this E with this to match or not? And also this d'origine, how do we want to search that? And moving on, we have this. Isn't this beautiful? So I'm not sure if I can read this, but I know Arabic, as long as you know that you start from the left and read to the right, maybe it should be okay, I don't know. But I can't read this. But it means that original Arabian coffee is considered a symbol of generosity among the Arabs in the Arab world. No, actually, I got this from a friend who actually is an Arabic native speaker who helped me construct this language. A friend of you too, I believe. Bushra. So, actually, this Arabic text here is also segmented by white space. So in Arabic, words are separated by white space. But in this example, this word here means original. And it has been elongated. So it looks like it's very long. It has a long line. And that's only a stylistic thing. So in a good search experience, we probably want to match this word with and without this elongated stylistic character. The Tatwel, is that what it's called? And then also, do we want to normalize these diacritics? You see all these like beautiful squiggly things around the texts. Do you want to normalize these? They are not typically used in contemporary Arabic. So if we normalize this, this becomes like this. But also in the case of Arabic, people don't always know how to write Arabic properly on computers. So this sentence actually contains some spelling mistakes. So, because in the Arabic language, all these diacritics, they are sort of optional, or they are implicit. The words, if you remove all of them, the word might change its meaning, but this ambiguity is typically understood implicitly by the reader from context. So even though these spelling mistakes are there, they are not so serious for the readers because they understand what this says anyway. But for a search engine that does text matching, this might be a big issue. So this third word over here, this is supposed to have 2 of these dots underneath it, and I believe there are some words here that should have 2 dots above it that they don't have. With Arabic, we also have interesting cases like, Arabic script is used in Arabic, but it's also used in Farsi and Urdu and other languages. Sometimes these glyphs, how these characters look, they look identical across these languages. But their Unicode code points are the same. So if you just do text matching, these words might not match even though they look exactly the same. So I have those complexities as well. So dealing with all this is not straightforward unless you know all these things and can build all these things. This is another example. This is something I know more about. JR 新宿駅の近くにビールを飲みに行こうか? Ike-san agrees. So basically means, shall we go for a beer near JR Shinjuku station? In this case, what are the words in this sentence? So which tokens do we index? We don't have any white space character that separates words in this case. So in Japanese, words are implicit. So the readers implicitly understand what the words are. But a search engine doesn't know that. So we need tokens to match and so on. So how do we find these tokens? So these are the actual tokens. And also in this case, do we want the word nomu to match nomi? So Japanese is a highly inflected language. So we have these verbs are highly inflected. So do you want an inflected form of the word to drink to match the dictionary form, nomu? And also do we want, this means beer, but it's written using half-width characters. Do you want that to match beer in full-width characters? And in Japan, people use a lot of phones and they use a lot of emoji, and maybe you want this beer emoji. That's a Unicode code point some Apple people are using on iOS, right? So you might even want that to match beer, depending on your application. So some of the common problems that we have seen here is that we need to segment source text into tokens for a search engine to match it. And we also need to deal with non-space separated languages. And we also need to handle punctuation in space separated languages. And we have also seen that with some Western languages like German, we have problems with compound nouns. And also applying some normalization is very helpful. for character normalizations, those characters with accents and so on. But also morphological or grammatical normalizations are relevant here. Sometimes spelling variations could be relevant, and also synonyms perhaps, but that sort of also depends on your application. So the key takeaway here is that natural language is very complex. Each language is different and it has its own sets of complexities. So we've only had a look at 5 languages, but there are many, many, many other languages out there with their own set of complexities. So good search needs per language processing, and there are many considerations to be made. Some of them might be application specific. So moving on, we're just briefly going to introduce some search quality measurements. Maybe most of you know this already, but we'll introduce the notion of precision, which is defined as the fraction of retrieved documents that are relevant. So if I want perfect precision from my search engine, then what do? According to this definition, I can just return a single relevant document, and then I have perfect precision. Precision equals 1. That's not very helpful as a measurement. So we also introduced the notion of recall, which is the fraction of relevant documents that are retrieved. So for any given query, then how can I get perfect recall? I just return everything. That's not very helpful either. But if we combine these two, we can get an accuracy measurement that is often called F, which is a harmonic mean of precision and recall. So in this talk, we'll talking a bit about how we can improve precision and also how we can improve recall. Usually improving one of these sets us back with the other. So in the context of search, it's also this measurement does not capture rank, where the order of documents occur in search results. So you have other measurements for that, like mean average precision and so on, but we're not going to talk much about that. But there are other, to measure ranks, there are other measurements out there that, if you're interested, you should be looking at. So one thing to ask yourself is, what should I optimize for? Precision or recall? Usually you can't have both. And the answer to that, I think, is that depends on your application. When you should optimize for precision, if you have lots of hits and several results can serve the user's information needs, you should optimize for precision. So just make sure the user can find a few good relevant hits rather than overwhelming them with lots of irrelevant results. So you'd probably make this sort of decision for applications like web search, knowledge management, and so on. But optimizing for recall, so if missing out on a relevant document is very important for your application, you should optimize for recall. You just make sure that you get all the relevant hits, and you probably get things that are not relevant, but you can live with that because it's so important that you don't miss any relevant hits. So for applications like compliance, patent search, digital forensics, and so on, you should probably optimize for recall. So in practice, though, a lot of this NLP tuning work is about improving recall without hurting precision too much. That's my experience, at least. So with that, let's look a bit into how linguistics work in Lucene and Solr. And I'll give the word back to Gaute.
So we will talk about the natural language capabilities and how to work with them in Lucene and Solr. And I will start talking a little bit about Lucene, and then Christian will talk a little bit about Solr afterwards. And well, as you all know, Lucene is a library which has the core functionality, and it's great for embedded things into your any kind of application. It doesn't have any configuration files or no schema or anything, and it runs on only a single server. But it has support from many languages, and typically program with Java towards the APIs. And Solr, on the other hand, is as you of course know, is a ready-to-use server, and where you can interface it through HTTP, and you can set it up in different ways, and you can have it scale up in fault-tolerant fashion with a lot of different functionality, advanced functionality facets, spell checking, highlighting, and so on. But internally, it uses Lucene for the search part. So I will start talk a little bit about the Lucene part of it. So a very simplified architecture of what goes on here is that we have a document when we index something, and we take it through Lucene steps in Lucene before we put it in the index. Same in the same fashion, when we have a query and we want to search something in the index, we also have to go through a similar process. So this process is called an analyzer, or an analyzer chain, and it analyzes the queries of the documents in a pipelined way, and before you index and search it. So the thing which is important here is that the Lucene just looks at one field at a time. So a document can have several fields, and here we are looking at each field at a time, separate process for each field. And this is where we have to work if we want to do something with linguistics in Lucene. So we call this an analyzer, or an analysis chain. And what does this actually do? So it takes text, natural text, as its input, and then it turns out to streams of tokens. And the tokens, they are produced by something by a tokenizer. And then you can process it further by applying all kinds of filters to add value or remove parts of it from the token stream. So very high level, this is what the analyzer looks like. You have typically a reader, which is where you get the text from the application that's going to go into the index or go for a search. And so the reader gets text in, and then it's sent to a tokenizer that provides it, that splits it up into separate tokens. So in the tokenizer, we will get a little bit back to the details, but the most interesting happens in something called in the increment token method. And should also be mentioned that before we get to the tokenizing steps, for some languages you might have a char filter. We are not going to go into details on that, but that might happen actually in the step. It might be associated with the tokenizer. And then after that, we can go through different kind of filters on the token stream. We can update things, we can change things, we can enrich the tokens, and again, the token filters have the same API and same. And the most interesting thing is happening in the increment token method. So we're going to go through an example. Oh, we have the French again. So I'll see if I can manage to get through it. So let's say we have this French sentence here, and we will just look at the French analyzer, which is part of Lucene, and see how it processes this text. So first, we send it to something called a standard tokenizer. And what it does is first, we see that it removes actually the dot at the end, at the end of the sentence, and it splits up all the words into separate tokens. So next, we have then we're on the next step where we start to apply filters to this to the tokens. This is something called an elision filter, and we can see here that it takes away this the d'origine, this D here with the apostrophe, and we see that there's a little change to the tokens. After that, we send it to a lowercase filter, and we see that the lowercase filter just takes all the characters and turns them into lowercase. And then we have something called a stop filter, which is used in many languages. And basically what it does, it takes away, removes all the words that are that they are used in so many contexts that it doesn't actually give any value to the search. So to remove noise from the token stream, we take away all these words in the stop filter. And after that, in French, they use something called French light stem filter, which takes the words and stems them, so that we can have variations of the same word, get a match in the index. So what have we done? We have the French analyzer. We've gone through all these steps, and we've turned the sentence on top to the 5 tokens at the bottom. So what? Just to sum up again, we have the standard tokenizer. This is very often used. It takes care of punctuation, and it's used for many space-based languages based on JFlex grammar. You have this elision filter, which removes the elisions from tokens. And we can actually see this is from the setup to Solr, that you have files that decide what kind of things will be removed and changed. And for French, it's actually located in this directory and this file in Solr. The lowercase turns everything to lowercase, and we have the stop filter. Again, it's also included. It's configurable by a file, and then we use the French light stemmer to stem the French words. So if we're going to look into more, we're going to look a little bit more into detail on the processing model here. And so the analyzers, they provide something called the token stream. And you can get to it by calling this token stream, which you have to call on the field, and you give it a reader that reads in the data. And the token stream actually bundles together all these tokenizers and prepares everything and with additional filters, so that you can go that you next can go to increment the token, to advance each token at a time, and do processing on it. So information about the token itself, it's provided by something called token attributes, and that are attached to the stream. And there are different attributes for the text in the term, the offset, and token type, and so on. And they are updated every time we call this increment token. So we're going to do a little bit of show some examples to explain this in code. We have prepared a few demo files that's available on GitHub, and we will just use these for examples. So I will not download it. We have it in this directory here. So I'll first go to the Lucene analyzer example, and actually we should probably have a look at the code. So this Lucene analyzer example has So we made a very simple. We're just using the test interface to something very simple. We take all these example sentences that we were discussing before. We pass them the correct analyzer, and then we just print out and see what happens. So as I mentioned earlier, we can have a look at the French analyzer, for example. Just see maybe. So the French analyzer here, which is the one we will use, it is, we can see here that there is a method called create components down here. So that's actually where the action is happening when it's chaining together all the different parts of the analyzer. So we see here that when you have this, when we create the stream, we get to this method which puts everything together. We have the standard tokenizer, this filter, license filter, lowercase filter, and so on. So, see. Yeah. So what we are going to do here in this example, we're just going to pass this analyzer to this print method so that we can just advance a token at a time and then just have a look at what happens. So this is a very simple example. We take all the streams, we just give it an analyzer. As I mentioned earlier, to get the token stream, is actually internally calling this the method I was just showing. We have to pass the field. We're not actually using it for anything right now, so we're just giving it a dummy name. We pass it the text, and then the first thing we do, we just prepare it. We're calling this reset method to prepare, starting to consume tokens. And then we add this char term attribute. So this actually is an attribute that we add to the stream so that every time we pass through a token, we will get this value back, which will show what the text is for the token. And then next, we just go increment each token and look at the results. That's basically it. So we can, we have, there are instructions on this, in this project, how to build things, but we can, so by running this test, we go through all these different examples, and we can see here, starting from English on top, we get the sentence, and we can see all the different terms, and what the result is after it's been going through the analyzer chain. Same for German. We see that German is removing more words, and so on, Arabic and Japanese. Okay, so next we have we're going to talk a little bit about synonyms. So we're just going to show a small example of what we can do. Let's say we want to provide our own processing, and we want to make a new analyzer that does something. So for this example, we're just going to introduce some synonym analyzer for French, and see how we can actually do that with Lucene. So why synonyms? They're quite flexible, easy to use, and they're very powerful for improving recall. And we have actually here, we have two ways, two types of synonyms. We have one-way mapping. For example, here you see that the sparkling wine is mapped to champagne, but not the other way around. And also, we have a two-way equivalence. The AOC is an abbreviation for the Appellation d'origine contrôlée, and so if we search for either term, we can get a hit with documents that has the other one, so on. So the synonyms, they can be, we can apply them either at index time or the query time. Usually you just apply it on one side, not both. And we can discuss whether it should be applied on index time or the query time, but best practice is usually to do it on the query side. So this allows a little bit more flexibility, and we can update synonyms and so on without re-indexing everything all over again. So I will just show a little bit of this example for doing this. So again, we're doing, we have another example here. This is basically very similar. We create some synonyms, a list of synonyms here, two here, then this one here, and then the sparkling wine to the champagne. We create a French synonym analyzer, and then we print the details for it. I will have a look at so the French synonym analyzer is the new analyzer that we have built. And as so it through the constructor here it initializes the synonyms, and what it actually does, there is this utility class to do synonyms in Solr. Solr synonym parser that parses the synonym terms and adds them to a map, and then we override this create components method that strings everything together. So we have here a standard tokenizer, lowercase filter, a synonym filter, which we give this synonym map, French light stem filter, and that's it. That's all the implementation for adding synonyms to this analyzer. So again, we can So again, we can run the code, and for this sentence here, we get a list of well, actually, I didn't show what we were doing. So we're doing basically this print method here. We are doing a little bit more than the earlier. The earlier one we were just adding one attribute. Now we are actually adding 3 attributes to the stream. We're adding the term itself, the offsets, and the type. And we're just printing it out. So we can see here that we have the sentence split up. We see here at this point at the offset 33, we have added a synonym for this DOC here. And so this means that these 3 words and this word is actually mapping to the same value all the time. So even though this is just 3 words, we have it at start offset 33 and the end of it set 64, which is the same as the other 3 terms combined. So with that, I will give the microphone back to Christian.
Okay, so I'm going to talk a little about linguistics in Solr, and also how it sort of differs from Lucene. So this is a very simple Solr architecture. You know that Lucene is a part of Solr and all that. And in this case, we're adding a document. So we have some XML that we're adding. We have our update request handler that handles input. So this XML gets converted to a Solr input document, and the update chains get activated. So here we have a document that has an ID, title, and a body. And Solr also has a concept of change processing things. On the document side, it's called update request processors. They are not so commonly used in Solr, but they are very useful in many, many cases. So these update request processors, they process a document at a time. So this document here with an ID, title, and body, that's processed as a unit. So as Gert mentioned, in Lucene, we are processing fields as a unit. So in Lucene, we just have a field and its value. We cannot look at other fields in the document. An analyzer is restricted to that single field. And that is a limitation, and that's probably by design. But that's a limitation of analyzers. So in this case here, we can look at this document. We can look at title and body and perhaps infer that this document has a genre. And we can add that to the document. So we can do that as part of an update request processor. And then when this document gets processed by Lucene, we process each field individually. So we process them individually. We have process ID first. Perhaps we don't do any analysis on ID. Title, we use some analyzer, and it goes through and we process it. Same with body. And with genre, perhaps we're using a different, simpler analyzer with with fewer filters in it, like this. And then this will be a document that we add to the index. So the important thing here to realize is that with Solr update request processors, we can process document as a unit and look at fields and add logic that produces new fields and reads other fields. We cannot do that in Lucene. So on the search side, we have a query coming in and go through search components and analysis chain, and results come back through. So I'm going to show you how we can do multilingual search with Solr using a Solr update requests processor to infer document language. And thereby, by inferring this language, we can apply the correct linguistics processing. Because as we talked about earlier, we need to handle languages separately. We need to process them separately and analyze them separately. So here I have, this is the Lucene Revolution 2013 repository. I'll go into the Solr multi-language example directory. I will unpack Solr 4.2.1 here. And then I have some configuration here that we're going to apply. So I'll show you first the Solr schema that we will be using. So I've added some dynamic fields to this schema. So Solr has a lot of field types defined for a bunch of languages. So this txt_AR, that's for Arabic, and txt_DE is for German. So this is the definition of the Arabic field type. So we have the standard tokenizer, and then lowercase filter, and the stop filter, and then do some Arabic normalization. So Solr actually has a lot of languages defined as field types. So that was added in Solr 3.6. I think it was one of the really important additions to Solr. This gentleman over there did a lot of that hard work. So thanks a lot for that, Robert. So we have all this language support now available in Solr as field types that we can just use. So that's what I've done. That's what I've done here. I've defined a dynamic field. So every field name that then _AR, that will use Arabic field. Same with German, French, Japanese, and Norwegian. So if some title _AR comes in and it's been added through the update chain, the Arabic language processing will be used on that content, similar with the other languages. So I'll also show you this language detection module that we will be using. So here I've defined a new update request handler that I've just called multilanguage. And this uses an update chain that's also called multilanguage. And this update chain has 3 processors. These 2 are just basically pretty much used all the time. But this thing here, this LangDetect language identifier update processor factory. So basically, what this thing does, it takes text from field's title and body and tries to figure out what sort of language this text is written in. automatically. That's pretty cool. So in Solr we have two of these. We have two language identifier. One is from Tika, and there's this one here that's developed by a Japanese guy. And this Japanese guy's version is really, really good. So if you're going to do this, use the Japanese version, the guy's version, and not the Tika stuff maybe yet. I think the Japanese guy's version stuff should go into Tika, but there's a Jira for that. So basically, by looking at title and body, this update request processor then writes or makes a new field that's called language with the language that was detected. We also have a fallback in case we cannot find a language. So we use English in that case. Perhaps that should be application defined. So we are not using this fallback if the confidence score that this guy returns is higher than 0.5. And this configuration directive here says that it maps fields. So if title comes in, it creates a new field that's called title underscore Arabic in the Arabic case, title underscore JA in the Japanese case, and so on. And thereby, we map these things into our schema, and Solr will apply the right processing. So I'm going to copy this configuration. I'll copy these two files to Solr example, Solr collection 1 conf. And then I'm going to start up Solr. Here we go. So we start Solr. And then I'm going to take these documents that I've prepared from Wikipedia. So we have 1,000 Arabic documents, or 1,000 documents from the Arabic Wikipedia, 1,000 from the German Wikipedia, 1,000 from the English, French, Japanese, and also the Norwegian Wikipedia. So we're going to index all those documents. So I have a small script that does that just posts these documents using this multi-language update request handler that is set up. So let's do that. So now all these documents are being posted, and this language identifier identifies language and does the field mapping based on the languages that it detects. So let's see, we have Solr here. Let's try to do a search and see what this guy has done. So we added this field languages, so let's just do a facet search on that. Or maybe we should do a facet search on, we also, as part of this input document, we have a field wiki that indicates the wiki that this document originates in. So here we have these facets. So we have 1,000 documents from the Arabic wiki, 1,000 from the German, and so on and so on and so on. We also have this field language that is the identified language. So what we can do here is we can search for, let's say, something from the Japanese wiki, and let's do a facet then on language. So this gives us all the documents that are in the Japanese wiki, and we facet the language that was detected. So we'd expect us to get a lot of Japanese stuff in there, right? And we do that. As part of those 1,000 documents, 998 of them were identified as Japanese, but 2 were English. That's peculiar. We'd expect maybe this guy's doing something wrong, or we can see what these documents are by doing a search. So let's say we add a clause here, and language. So we're searching for the English documents now in the Japanese Wikipedia. And let's say we return some hits. See what's there. Okay. So we found 2 hits, which we expected. So this is our first result. Well, this is some English text and there's some Japanese text in here, but this is detected as English, and English processing was applied. So here we're also seeing a second hit, and that looks like the GPL, which is in English. So if we had just indexed these documents and applied only Japanese processing on this content, we wouldn't be able to handle this English content properly. We would have treated it as Japanese, basically. And that would be a problem. So in this case, this language identifier helped us a lot because it helped us apply the right processing. But it's not perfect. It's not perfect, but it's very good. Its accuracy its F is higher than, I think is around 0.99. So it's very accurate. Mike McCandless did a test of some of these open source language identifiers. You can see that on his blog. But let's see. I also added some Norwegian content in there. And the reason for that is I want to see how this language identifier performs on Norwegian content. Norwegian is very close to the Danish language. Written Norwegian and written Danish, they're very close. So I want to see how confused it gets, or if it gets confused. So let's try that. Let's search in the Norwegian wiki, and let's just facet by language and see what's there. Okay, let's remove these hits. Let's just get to the facets. So this is what we get. Of those 1,000, 977 is classified as Norwegian, 18 are Danish, 4 are English, and 1 is German. So we can find what's this German document there. Is there really a German document there? Let's see. This is not a good document. It seems like to be a list of mathematicians. So, and this was classified as German. There are. But this is an example of junk document, and the was that it was classified wrongly. But I can look at these documents that are Danish, perhaps. It says historical events on these days. If you prefer the year in a less compact format, : and then. So I think this phrase is identical in both Danish and Norwegian. But this was classified as Danish, but it's not. This is Norwegian. So in this case, it can argue that it made a mistake. Do you know, Gaute, if this is also perfectly valid Danish? Not sure. But this works pretty well. Okay. How are we doing on time? Okay. So moving on. Solr has a lot of language supported out of the box as field types. So these are some of the languages, not all of them. Some Polish stuff is also available, but it's not defined in schema XML. So all this stuff is available that you can use. So you define your field with these field types, and you can use this. You can use analyzers to process this language. So Korean is not there, but that's coming soon. We got a code donation for a Korean morphological analyzer. That's in Lucene 4956. So that's coming soon. So a little bit about the NLP ecosystem. So there are also really, really high quality commercial text analytics software out there. So there's a company called Basis Technology. There are people from Basis here. They have a booth out there, and they have really good technology. So I encourage you guys to visit their booth and talk to them and see if some of their technology is a good match for what you need. So this is sort of high-level overview of some of the things they do, but talk to them. They have lots of cool stuff, and they are nice people. They're also our customer. So, but don't take my word for that their stuff is so nice, but have a look yourself and make up your own mind. Their stuff also integrates well with Lucene and Solr. There's an Apache OpenNLP project, which is a machine learning toolkit targeted towards NLP. So it implements a range of common and perhaps best practice algorithms. Perhaps these guys do not implement the leading, bleeding edge best algorithms, but it's useful. And it's very, very easy to use. So it does tokenization in somewhat a different way than tokenization for search, perhaps. It also does sentence segmentation and part of speech tagging. It does named entity recognition to extract names from free text. It does chunking, and it has a nice license. So the code has this Apache license, but its statistical models, they are available for download from SourceForge, but quite frankly, I don't know what licensing terms apply and what F-scores they have, how good they are. There's a Jira to integrate OpenNLP in a Lucene analyzer framework. That's work in progress. That's not completed. Skal vi skippe den eller? So there is we also have a tutorial that shows how to do some basic text processing with OpenNLP. Maybe I can just run that very quickly. Just run the example. So we are just running a few examples here that takes this text and segments it into sentences. And so you can see that it is smart. It doesn't break a sentence where it looks at this dot here, and it can also take this sentence and it automatically identifies Bill Gates and Paul Allen as persons in this text. And this is some texts that we also tokenize, and we also do part of speech tagging. So you can see the part of speech for each of these tokens. So if this is a noun phrase and so on. And this is the probability that this model gives us with this text. So that stuff's on GitHub. You can have a look. So these are other ecosystem options that you can have a look at. There's Stanford NLP. It has a GPL license, some commercial license available. There's Gate GPL with commercial licensing. There's WEMA and Clear NLP. These are other things that might interest you. We don't have a lot of time here. Just to summarize quickly, getting language right is hard. And linguistics is important for good search quality. And yeah, I'm not going to just read what this says, but to sort of look at things in the bigger picture, I think it's very, very important that you understand your content and your users' needs, and also understand the language that you're using and what their issues are. If you're having issues with recall, consider synonym stemming, consider the word delimiter filter, and also phonetic matching. If you have issues with precision, perhaps you consider ANDing terms instead of ORing them. Perhaps you should look at improving content quality, searching fewer fields if you're searching many. If some content is more important than other content, just maybe you can consider boosting that content with a boost query. Some thank yous. The example code is available on GitHub. If you have questions, just email us or contact us here. Q&A, very briefly. Anyone? I'm not sure there is a... The question is how if you have one language, content in one language, and you want to search that content using other languages, I'm not sure if... I don't really know a best practice for that. I have some ideas of what can be done with transliteration and so on, or queries, but I'm not sure how well it works. It's a very hard problem, I think. The standard technique for dealing with documents that are multilingual. That's also tricky. I'm not sure what the best way to deal with that would be. The language identifier that we have talked about today cannot detect sort of the bounds within the language bounds within the same documents. I think that basis stuff can do that. But
then what do you do?
Exactly, what do you do, right? So I think the short answer is I don't really know. I have a good answer to offer. So I might run. Have I run 10 minutes off? Yeah. Okay. Thanks a lot, everybody.